Today we are going to talk about bridge pattern. Let's straight away start with the stack implementation. Suppose we want to implement a stack. We got to have a base class called stack. The base class stack is going to define the interface to the stack. And the interface to stack is two methods, push and pop. As you all know, push takes an integer and pushes the integer into the stack, while pop returns you the last integer on the stack. There are two ways in which we can implement a stack. One is using arrays. So what we would do is we would derive a class called arrayStack from this base class called stack. The arrayStack class has two methods, push and pop. And these two methods are going to work on an array of integers which is called as element. And as you can see in this picture, this array of stack allows a maximum of max elements. We also have one more variable called top, and this top points to the top of the stack. There is another way to implement stack, and that is using linked list. So what we would do is we would derive another class called llStack from the base class stack. Now llStack derived class has to implement push and pop again. llStack has a pointer to node star object. So node is representing each and every element of the stack, and the node objects are going to be chained in a LIFO purpose, and top points to the top of the stack. So this class diagram explains how we are going to implement a stack. What are the problems with this stack implementation? There are two problems with this stack implementation. Suppose we start writing the code for this stack implementation. How many header files and C++ files are we going to have? Normally, we would have one header file called stack.h. This stack.h is going to contain the class definition for stack, the class definition for arrayStack, and the class definition for llStack. And the other file called stack.cpp would contain definition for all the methods of the stack class, all the methods of the arrayStack class, and all the methods of the llStack class. So if a client wants to make use of this stack library, what we would normally do is we would compile stack.cpp and create an object file called stack.o, and the stack.o object file is going to be put in a library. Suppose we call that library as libstack.a. Now what client has to do is it has to include stack.h. It has to create one of the arrayStack object or the llStack object, and then call the push and the pop operations of that. So the file stack.h has to be made available to the client, which means that just by looking into stack.h file, it is possible for the client or the third party to find out details about how the stack is implemented. That is first problem. The second problem is if anything is modified in stack.h. For example, tomorrow we want to enhance this stack to include some kind of stack accounting which keeps track of, for example, how many push and pops are done. So we will have to go and modify things in stack.h. And any modification to stack.h means that not only the library libstack.a has to be recompiled, even the client code has to be recompiled. So these are the two problems with the stack implementation. So now we would try to solve these two problems by implementing stack using the bridge pattern. Let's look into how the class diagram would look like. So what we see on the screen right now, we have three classes: stack.imp, arrayStack.imp, llStack.imp. This is exactly the same as the solution which we saw, which was just 2 slides before. The only difference is that instead of calling the class stack, now we call the class as stack.imp. Instead of calling the class as arrayStack.imp, instead of calling the class as array stack, we are calling it array stack IMP, and instead of calling the class as LL stack, we call it LL stack IMP. Now, in addition to these three classes, we are going to introduce one more class called stack. The class stack, which is on the left side, has a method push pop. It has a constructor which takes the type of the stack which needs to be created. And the last element of the stack is a pointer to the stack IMP object. So the idea here is the class stack is going to specify the interface. This is going to be interface to the client, and the stack IMP is going to implement it. How are methods like push and pop of the stack going to be implemented? The methods push and pop of the class stack would just take the pointer IMP and invoke the method push and pop. And the constructor stack type, it takes a type parameter from the client and it creates the array stack IMP or the LL stack IMP depending on the value of this type. The second solution raises a lot of questions. The first question is, how does the above implementation prevent implementation details to be shared from the client? Question number 2. Does solution 2 solve the problems of solution 1? Who decides whether to create array stack IMP or LL stack IMP? Solution 2 solves some problems present in problem 1. But what is the essence of change we have done? And so which class provides the abstraction now and which class implements it? Let's look at these questions. So how does solution 2 above prevent the implementation details to be shared? So in this case, we are possibly going to have 4 files. In the second solution, we are going to have 4 files. One is going to be stackimp.h. The other is going to be stackimp.cpp. Then we would have a stack.h and stack.cpp. Out of these 4 files, all we got to share with the client is the file stack.h. The other header files can be internal to the library. And just by looking into stack.h, it is not possible for client to find out how the stack is implemented, because we would expose only the public methods of the library, which is push and pop. The other methods like element or the node star top, these are pretty much inside stackimp.h, so these remain to be hidden from the client code. Second question, does solution 2 solve the problems of solution 1? Yes, it does. The first problem with solution 1 was the implementation details were exposed, and as we have already discussed, the implementation details with solution number 2 are not exposed. And a change in stack implementation does not require client code compilation. Assume this class has to be changed to do accounting of push and pop operations. So the only change which has to be done is in the method in the file stackimp.h and the stackimp.cpp. Nothing gets changed in stack.h. And if nothing is getting modified in stack.h, the client code need not be compiled again. Only the libstack.a has to be compiled and so created. The client of course has to be linked. So the solution number 2 does solve both the problems which were present in solution number 1. The next question is, who decides whether to create array stack IMP or LL stack IMP? As we already talked about it, the constructor of the stack class takes a type parameter, and so it is the client who is specifying whether you want the array or the linked list implementation of stack. It is also possible that the stack class does not take a type information from the client, and based on its own logic, it could be environment variable, it could be some database attribute that it decides whether it has to create the array stack IMP or the LL stack IMP class. So what is the essence of the change which has done in solution 2? So the essence of change is the solution 2 basically decouples an abstraction from the implementation. What we saw on the right side was the stack implementation, and what we saw on the left side, which is the stack class, that is an abstraction. In solution number 1, the abstraction and implementation were very tightly coupled. In solution number 2, the abstraction is decoupled from the implementation. So now, which class provides the abstraction and which class implements it? The stack class provides the abstraction and stack IMP and its derived classes they implement it. So let's get into some theoretical stuff about bridge pattern. What is the intent of this pattern? The intent of this pattern is to decouple an abstraction from its implementation so that the two can vary independently. The first part, which is decoupling an abstraction from its implementation, is something which we understand. Now the second part, which is these two can vary independently, is something which we are going to see more in detail. This is how the structure of the bridge pattern looks like. Let's look at the right side of the picture. We have an implementer class and two derived classes called concrete implementer A and concrete implementer B. So this hierarchy of three classes, which is concrete implementation A and B derived from implementer, is the implementer. This is going to implement the methods, and the method which is implemented in this case is the operation IMP. On the left side, we have an abstraction class and the refined abstraction which is derived from the abstraction class. Now the left part of the picture, which is the abstraction and the refined abstraction, this implements the abstraction. And as you can see, the abstraction class contains a reference to the implementer, and the method operation of the abstraction invokes the operation IMP of the implementer. So it basically forwards the request to the implementer. So who are the participants of the structure? There are three participants. One is the abstraction, like in case of stack. Now this abstraction defines the abstraction interface. It maintains a reference to the objective type implementer. The implementer defines interface for implementation class. This interface can be quite different from abstraction class. And then we have concrete implementer, which is array stack, and this class implements the implementer's interface. Question: how does bridge pattern differ from proxy pattern? In proxy, as we see in the last lecture, the proxy also seems to pass on the request to the real object, and in addition to passing on the request to the real object, it can do some extra work. So in proxy, both proxy and real subject derived from the same base class, and they have the same interface. But in bridge implementation class need not have the same interface. That is the fundamental difference between a proxy pattern and a bridge pattern. Okay, more questions. The benefit which I see from example number 1 does not sound strong enough for me to use in my application. After all, I am not a library designer. How else can I get benefited from bridge pattern? So use the bridge pattern when you need to create the abstraction object but not the implementation object. Which means that I want to create the stack object, but I don't want to create the implementation object. This is not possible in solution number 1, for example, for the stack, because the abstraction is very closely coupled with the implementation. And when the implementation must be selected or switched at runtime, even in those cases use the bridge pattern. Now let's look into the pilot classification example from MM and how that uses a bridge pattern. This picture shows that there are two MM1 and MM2. MM1 has two BTSs inside it, BTS1 and BTS2. BTS1 has 3 sectors. BTS2 again has 3 sectors. MM2 has only one BTS called BTS3, and this again is associated to these 3 sectors. Now suppose we have a mobile which is somewhere here, and it is already on a voice call with the network which is going through BTS1. Now as this mobile approaches the border area towards BTS2, it notices that the pilot of BTS2 is becoming stronger. Now what is a pilot? Now every sector in CDMA is represented by one pilot PN offset. So, and the mobile continues to receive the pilot information, and it can measure the strength of the pilot. So when it wants to do a soft act, the mobile is going to send a message to the network telling about the PN, the neighboring PN, and its strength. So a pilot, as you already said, represents a sector in CDMA1X. Now let's look at right side of this picture. A pilot can be a local pilot or a pilot can be a remote pilot. If you have a pilot which is associated to a sector on BTS2, then it would be a local pilot because the call is on BTS1. But if the mobile sends information about a pilot which is on BTS3, then this pilot, as seen from MM, is going to be a remote pilot. So the right side of the picture shows a pilot classification hierarchy. It also says that the method attempt candidate add, which is an operation, the implementation of that is going to be different for a local pilot and remote pilot. Because for a local pilot, we would probably just send a message to the BTS. But for a remote pilot, when you try to add that leg on the other BTS, BTS3 in this case, you have to send a message to MM2. Now that is right part of the picture. Now the left part, which is the pilot and the pilot data class, basically implements the abstraction class, something what we had the stack class. The only thing is, instead of having just one class, it has been split into two classes. The pilot implements the abstraction and the pilot data stores the data of the pilot. So the data of the pilot are, one is the pilot P and offset, which is just an integer number representing a sector, and it can also be the strength of the pilot. So this is how the class hierarchy is maintained for the pilot data object. Now when you do a soft handoff, it basically has three steps. The first step is to parse the handoff recognized message and populate the pilot data. At this point, we don't know who is the implementer will be. The implementer can be the local pilot or the remote pilot class. But when we parse the HO recognized message, we would get the pilot information, like the pilot P and offset and the strength of the pilot. So at this point of time, we would extract this information from the HO recognized message, create a pilot data object and store those information in the pilot data object. So this is represented in this hierarchy. We have a CDMA handoff object for every call, and the CDMA handoff object contains another list which is called as internal candidate list, and this has an array of pilot objects. Now when we parse the HO recognized object, we would take the can pilot 0 and new up a pilot data object and put the pilot data in that. At this point of time, at the end of step 1, we are not going to create a local pilot or the remote pilot object. Then we come to the second step. So as a part of second step, we determine if the candidate pilot is a local pilot or a remote pilot based on some database lookup. And then we create a local pilot or remote pilot object and then put the pointer of that to the pilot object, which is this. And then we call the method attempt candidate add, because once we figure out from the database lookup that this is a local pilot or remote pilot, then we know which method has to be implemented. The pilot class and the pilot data class is an abstraction. So the third step is, once the execution of attempt candidate add is done, which basically means that in a very simplistic description, the candidate has been added. The third step is to create an active circuit pilot object and point it to the pilot data object, which is shown in this picture. Now this part was already created, the pilot data and the pilot data pointing to the local pilot or the remote pilot object. Now this pointer is made to point to the active circuit pilot object, and that is the end of call setup. So as you can see, this pilot hierarchy makes use of the bridge pattern. The three classes on the right side, which is pilot classification, including local pilot and remote pilot, implements the implementation, and the class on the left side, which is pilot, implements the abstraction or the interface. Now applicability of bridge pattern. So above example illustrates that use the bridge pattern when you need to create the abstraction object but not the implementation object. As we saw in the pilot example, we had to create the pilot object and the pilot data object when we were parsing the HO recognized message, because we had to get the pilot information from the message and sort those pilot. But at that point of time, the implementation object cannot be created because we don't know whether this is a local pilot or a remote pilot. So this So the idea here is to avoid a permanent binding between an abstraction and its implementation. And use bridge pattern when implementation must be selected or switched at runtime. So this again is illustrated in example number 2. The selection of the implementation, whether it is local pilot or remote pilot, is done at runtime based on the content of the HO recognized message and the database settings. So the implementation is, if the implementation has to be selected or switched at runtime, then in that case the bridge pattern has to be used. And then we had two applicability of bridge pattern from the stack example, which is hide implementation from the client and change in implementation needs no client code compilation. Now question, can you design pilot classification without using bridge pattern? The answer is of course yes. If only pilot classification hierarchy is there, if only pilot classification hierarchy is there, where are we going to keep the pilot data, like the PN offset and the PN strand? They can't be in the hierarchy because in pilot and the pilot data objects are created, we don't know if it is local pilot or remote pilot. We can of course create duplicate copies of pilot data, one in pilot data and the other in pilot classification, but then it causes unnecessary data duplication and copy. So we saw 4 reasons when we can possibly make use of bridge pattern. Another scenario when you would want the bridge pattern to be used is to prevent proliferation of classes. Now we saw one, there is one class hierarchy on the left side, which is a window class, and then from this window class we have 2 derived classes called X window and the PM window. Now this window provides services like draw a line, draw a rectangle and stuff like that. Because we want our code to be generic for all platform and we want our code to work for for multiple platforms, so the methods draw line, draw rectangle has to have a different implementation for an X window platform and a different implementation for the PM window platform. Now suppose there is a change in software. There is a new type of window added. Let's call that as the icon window. Now this icon window provides the same function, which is draw line and draw text, but it is going to have an iconized view of that. So we would derive icon window from the window class, but then icon window again has to be implemented for both X window and PM. So there has to be 2 more classes called X icon window and PM icon window. So if you go for this approach, which you would normally do, the problem is proliferation of classes. And to have a more elegant solution, what we can do is to split this class hierarchy into 2 parts. And this is what we are going to do. On the right side, we have the Windows implementation class and the X window implementation and the PM window derived from that. This class has 2 methods. One is draw text, def draw text, and the other is def draw line. And these 2 methods are implemented by the derived class. And as you can see over there, the def draw line of X window IMP calls the X draw line, because these 2 methods are going to be implemented differently for the X platform and for the PM platform. The hierarchy on the left side contains the application level logic. The window base class has 2 derived classes. One is icon window and the other is transient window. And this shows that there are 2 kinds of windows which are possible. Now the methods draw text and the draw board. Let's look at this draw border. Now draw border is going to invoke draw rectangle and draw text, and draw rectangle eventually is going to invoke the draw line and the draw text. So eventually the methods of the implementation classes are going to be invoked. So as you can see, there are 2 inheritance hierarchy, one on the right side and the other is on the left side. And the hierarchy on the left side contains the application level logic, and it goes and implements the methods of the right class, the Windows implementation. We have a similar class hierarchy explosion for a thread scheduler. Assume I have a thread scheduler class. Now there can be multiple scheduling algorithms, so I had two derived classes. One is called as a preemptive thread scheduler and the other one is the time slice thread scheduler. These two schedulers has to be implemented for multiple platform because I want my code to be platform independent. So from the preemptive thread scheduler, there are three derived classes. One is Unix PTS, the other is JVM PTS, and the third is the window PTS. Similarly, from the time sliced thread scheduler, we have three classes derived. One is the Unix TSTS, the other is the Windows TSTS, and the third is JVM TSTS. Now suppose you add a new scheduling algorithm, you need to add one more class over here, and then there has to be three more derived classes from there. So this approach is again causing a proliferation of classes. So what the bridge pattern suggests is, instead of having this huge hierarchy, we can have two parallel inheritance hierarchy, and we can use the bridge pattern for that. So for the previous example, this is how we would change things. On the right side, we would have a thread scheduling implementation class, and for this thread scheduling implementation class, we would have two derived classes. One is for the Unix operating system, which is Unix PTS, and the second one is for the Windows PTS. Now this class is going to have methods which are specific to the platform. On the left side, we have a scheduler hierarchy. The base class is the thread scheduler, and thread scheduler has two derived classes. One is the preemptive thread scheduler and the time slice thread scheduler. So this hierarchy on the left side is going to contain the algorithm, the scheduler algorithm, something which is going to run at the application level. And then when it has to do something at the platform level, it is going to forward the request to the implementer object, which is on the right side. So let's summarize. When we would use a bridge pattern, or what are the advantages of bridge pattern? So the advantage of bridge pattern is it hides the implementation from client, and this is something which we saw in case of example number 1. The second advantage is a change in implementation needs no client code compilation. This is again something which we saw in the first example. If there is any change in stack.imp.h, the client code does not need to compile, it only has to be linked. Use the bridge pattern when you need to create the abstraction object but not the implementation object. And this is something which we saw in our second example. It was important for us to create the pilot and the pilot data object when we were parsing the hand of recognized message. But when we were creating pilot and pilot data object, at that point of time, we did not know who is going to implement attempt candidate add. It could have been implemented using local pilot, or it could have been implemented using remote pilot. So avoid a permanent binding between an abstraction and its implementation. When implementation must be switched or selected at runtime. So use the bridge pattern when the implementation has to be selected or switched at runtime. Again, the second example summarizes this well. And the last advantage or scenario in which we would use bridge pattern is to prevent proliferation of classes, which we saw in case of thread scheduler. Thank you.